Good evening, everyone. We continue with our class and move ahead. We have discussed till the refraction of light. So we have also discussed the importance of refractive index and we have understood the concept of refractive index. So absolute refractive index of a medium is simply called its refractive index. So refractive index of water, let us take the example of water. So it is denoted by this symbol and W. This is the refractive index of water and it is 1.33. So what is the meaning of the statement that refractive index of water is 1.33? There is a formula. Refractive index of water is equal to speed of light in air. This is 3 into 10 to the power 8 meter per second divided by speed of light in water. When we do this division, we get 1.33. So refractive index of ground glass is 1.52. How do we decode it? This simply means that the speed of light in air divided by speed of light in ground glass will yield a value of 1.52. Ability of a medium to refract light is expressed in terms of optical density. It is not same as mass density. So what is the ability of a medium to refract light? It is expressed in terms of optical density. An optically denser medium may not have greater mass density. Example, kerosene is optically denser than water, but its mass density is less than water. Okay. So here what is important to understand is the concept of refractive index, which we have understood. That refractive index of a material is calculated as the speed of light in air divided by the speed of light in that particular medium. So in case if we are saying refractive index of water is 1.33, that means speed of light in air divided by speed of light in water is 1.33. Let's move ahead and try to understand what really happens in refraction. The terms rarer medium and denser medium actually mean optically rarer medium and optically denser medium. Medium of larger refractive index is optically denser. So when light is traveling from denser to rarer medium, the light bends away from the normal. And when the light is traveling from rarer to denser medium, the light bends towards the normal. ठीक है. Medium of lower refractive index is optically rarer. So speed of light is higher in a rarer medium. Why? Because when the medium is rare, we can imagine like lesser people are there, so it will be easy for someone to run in a less crowded place. But if that place is jam packed with people, denser, it will be a little difficult. Same concept we apply here, that the speed of light is higher in a rarer medium. So obviously light will get a lot of space, it will easily run. So a ray of light traveling from rarer medium to denser medium will go fast and it will slow down in the denser medium and bends towards the normal. When it travels from a denser medium to a rarer medium, it speeds up and bends away from the normal. Okay. Now let's move ahead and try to understand the refraction by a spherical lens. A transparent material bound by two surfaces of which one or both surfaces spherical forms a lens. See, these are different types of lens. Lens are used in a microscope. Lens are also used in our glasses that we wear. Lens are also used to see the larger image of certain objects. So there are different types of lens. The glasses used in spectacles and magnifying glass used by watchmakers are examples of lenses. In a lens with only one spherical surface, the other surface would be plane. So what are the different types of lens? Plano-convex, plano-concave, biconvex, biconcave, and meniscus. Okay. Now what we will see is we will try to understand the refraction by spherical lenses. A lens with two spherical surfaces bulging outward is called a double convex lens. See, this is a convex lens. It's a lens with two spherical surfaces bulging outwards. It's called a double convex lens. Simply a convex lens. It is thicker at the middle than at the edges. Such lenses converge light rays. So it is also called a converging lens. See, in case of mirror, concave mirrors are converging light, but it is the reverse in case of lens. A convex lens is converging light. Okay, and a concave lens is diverging light. Okay, a double concave lens is bounded by two spherical surfaces curved inwards. As we can see, they are curved inwards. It is thicker at edges than at the middle. Such lenses diverge light rays. So they are diverging the light rays, concave lens. Okay. And in mirrors, convex mirror are diverging light rays, but in lens it is the opposite. Concave lens are doing the diverging action. So they are also called diverging lens. Okay. Let's move ahead. A convex lens or concave lens has two spherical surfaces. Each of them forms a part of a sphere. The center of these spheres are called centers of curvature of the lens, C1 and C2. Okay. An imaginary straight line passing through the two centers of curvature of lens is called its principal axis. This is the principal axis. Okay. The central point of a lens is called its optical center. Okay. Converging action of convex lens, diverging action of concave lens. A ray of light through the optical center of a lens passes without any deviation. The effective diameter of the circular outline of spherical lens is called its aperture. Aperture is just the size of the mirror, we can say like that. Okay. Thin lenses with small aperture. The lenses whose aperture is much less than its radius of curvature and the two centers of curvatures are equidistant from the optical center. So this is converging action of convex lens, diverging action of concave lens. Okay. Incidence of parallel rays on a lens. See, sun is on convex lens. It is giving the converging action. All the rays are going on a piece of paper and sometimes they burn the paper also. See, the paper gets burnt. Using a convex lens, focus the light from the sun on a paper. Obtain a sharp, bright, real image of the sun. Hold the paper and lens in same position for a while. Paper begins to burn and catches fire. The parallel rays of light from the sun are converged by the lens at sharp bright spot on the paper. It generates heat and causes burning of paper. Okay. Now let us see incidence of parallel rays on a lens. When several rays of light parallel to the principal axis fall on a convex lens, they undergo refraction from the lens and converge to a point on the principal axis. This point is called the principal focus on the convex lens. See where they have all converged is called the principal focus F1, and the length from center of curvature till focus is focal length. Light rays converging, convex lens, parallel rays, principal axis, focus. Now this is the concave lens. Parallel rays have gone, it has diverged the light and principal axis is there. So the image will be formed by taking these light rays behind, in front of the mirror. Okay. When several rays of light parallel to the principal axis fall on a concave lens, they undergo refraction from lens and diverge from a point on the principal axis. This point is called the principal focus of the concave lens. Okay. Now, if there is an incidence of parallel rays on a lens, okay, if parallel rays are passed from the opposite surface of the lens, another principal focus is formed on opposite side. A lens has two principal foci, f1 and f2. Same thing. Convex lens converged behind. Okay. Concave lens diverged and focus behind. First principal focus of concave lens, first principal focus of convex lens. The distance of the principal focus from the optical center of lens is called its focal length f. Okay. The distance between position of convex lens and position of image of the sun gives approximate focal length of the lens. Okay. Let's move forward. Image formation by convex lens. Take a convex lens, find its approximate focal length. Draw 5 parallel straight lines on the table such that distance between successive lines is equal to focal length of the lens. Place the lens on center line such that the optical center of the lens lies just over the line. The two lines on either side of lens correspond to f and 2f of the lens respectively. Mark them 2f1, f2, f1 and 2f2 respectively. Like this you have to mark. Place a burning candle far at 2f1. Clear sharp images formed on screen placed at f2. Okay, we can see an image formed, okay, of the candle at f2. Repeat this activity by placing object just behind 2f1 between f1 to f1 and f1 between F1 and O. Okay. So image formation by convex lens again. We have 6 cases similar to how we were getting in concave mirror. Same with convex lens. We are getting six cases. Okay. Nature position and relative size of image formed by convex lens for various positions of the object. See, at infinity, if you keep the object at infinity, image is formed at f2 and it is highly diminished point size, real and inverted. This table is important and it should be memorized by the students. Beyond 2f1, if you keep the object beyond 2f1, image is formed between f2 and 2f2 and the object is diminished, real and inverted. If the object is kept at 2f1, position of image is 2f2, same size, real and inverted. Between f1 and 2f1, beyond 2f2, enlarged, real and inverted. At focus, at infinity. Object is at focus, image is at infinity. Infinitely large or highly enlarged, real and inverted. Between f1 and O, on the same side of lens as object, enlarged, virtual and erect. So, image formation by concave lens. They are just two. Just like we have for convex mirror, 2 cases. Same way we have for concave lens, 2 cases. Place a burning candle on one side of concave lens. Look through the lens from other side and observe the image. Image will not be obtained on screen but can be observed through the lens. Move the candle far away from lens. Image becomes highly diminished. Nature, position and relative size of image formed by concave lens for various positions of the object. If you keep the object at infinity, image will be formed at f1, highly diminished, point size, virtual and erect. If the position of object is between infinity and O, object is formed between f1 and O, diminished size and virtual and erect. Okay, till here we have understood. Now let's see, a concave lens always gives virtual, erect and diminished image irrespective of position of the object. Wherever you keep the object, a concave lens will always give us a virtual and erect and diminished image. Okay. Now we see image formation in lens using ray diagrams. Like, what are the different rules? A ray parallel to the principal axis after refraction from convex lens passes through the principal focus on the other side of lens. For concave lens, it will diverge and go backwards. Okay. They appear to diverge from principal focus on the same side of the lens. Okay. F1 in case of concave and convex F2. A ray passing through the principal focus after refraction from convex lens emerges parallel to principal axis. A ray of light appearing to meet at the principal focus of a concave lens after refraction emerges parallel to the principal axis. Okay. A ray passing through optical center will emerge without any deviation. So till here it is clear. And now these are some of the diagrams of the convex lens. The ray diagrams for position, size and nature of image formation in convex lens for few positions of the object. Just it is similar to the table. The table that we see, it is similar to the table. Now we have placed the object at infinity. The ray of lights are coming, striking the convex lens, getting converged and image is formed f2 point size. Now object is kept beyond 2f1. One ray of light is hitting the convex lens, converged, other point straight. Image is formed, real and inverted on the other side. Same thing, 2f1, again converged, optically straight, a real and inverted image is formed. Now the same thing happens when the object is kept between 2f1 and f1. Image is formed somewhere below and it is real and inverted and enlarged in size. If it is kept at f1, image hits the mirror and the ray gets converged like this and the other one goes straight. So image will be formed somewhere at infinity and it will be extremely enlarged. Now if the object is kept between f1 and b, one ray of light goes like this, other one gets converged and passes through f2. When you take both the rays behind, a very enlarged image is formed and it is real and it is formed behind the object. So for this session, let us stop here. Let us keep the understanding till the ray diagrams of the concave lens. Thank you everyone for joining in this session.